So when dealing with molecular bonds or covalent bonds, again, typically speaking, they are nonpolar bonds, especially when you're dealing with carbons and hydrogens. But you run into things like water, where there is a significant difference in what's called the electronegativity of the atoms, and that creates a dipole moment or a polarity to the molecule. Okay, so we're going to talk about how to identify this polarity. Just so you know, this is it's a spectrum sort of thing. So we've got, down at this end, we have our nonpolar. And then as electronegativity differences increase, eventually you hit polar atoms. And then if it continues, and we'll look at a chart that actually gives you some numbers to see these differences, when you get into ionic compounds, which are no longer covalent, okay, so it's kind of like through here we consider covalent. Once the difference becomes enough to actually become ionic and transfer the charge over, then it's no longer a polar molecule, it's an ionic molecule. Okay, but polarity is when the atoms share their charge unequally. Okay, so those electrons in that bond aren't actually shared 100% equally. So, again, polar versus nonpolar. It's all about sharing those electrons. If they're shared pretty much equally, we call it nonpolar. If there is a significant difference in one atom's pull for the electron than the other, then they are called polar. Okay, so polarity is when, let's say the oxygen on water tends to hold on to the electrons a little bit more than the hydrogens do. Okay, a couple of things that help determine polarities. You can still have molecules with differing electronegativities, but if they have the right amount of symmetry, it'll still be nonpolar. So there's two things that we're going to look at here. We're going to look at how well they're sharing their electrons and also their shape and what kind of symmetry they have. Okay, so the shapes we just talked about are going to come in handy here. So if something is asymmetric, you tend to end up having a polar molecule because there's an atom somewhere that's not balanced by another one. Okay, whereas symmetric molecules are always nonpolar because all of the pull cancels out. So, key thing to determining, first off, whether it's even possible to have a polar molecule is electronegativity. Okay, and we talked about this once quite a while ago, but electronegativity is the ability for an atom to take another atom's electron. Okay, when you have when you have extremely large differences in electronegativity, you actually get electrons being stolen, completely taken by one atom from another, and that's an ionic bond. But within covalent bonds, when there's a slight difference in their electronegativity, you get a polar molecule. Okay, and this forms what we will call a dipole moment, or essentially an arrow that tells you which direction or which atom the electrons are hanging out around more. Okay, something to keep in mind is that the electronegativity increases as the radius of an atom decreases. So if you remember way back when we were talking about periodic trends on the table, you go to the right on the table or up on the table, radius decreases, okay, and electronegativity increases. Right, with fluorine being your most electronegative atom. So that's always a good one to remember. Fluorine almost always forms a polar molecule with whatever it bonds with. Again, when you get into shapes, that sometimes doesn't fall true, but as far as the electronegativity goes, it's going to try to. So, this table here is a list of the electronegativity of all atoms. Okay? So, you'll notice things like, sodium chloride. we have 0.9 electronegativity in sodium and 3 in chlorine. That's a huge difference in electronegativity, and that's why that forms an ionic bond. Whereas you look at oxygen, which is 3.5, and hydrogen, which is 2.1, that's not as big of a difference. So that's where we get a polar molecule. Okay. So again, there'll be some rules that we apply to this, but this table, you might want to take a screenshot of it, or there is a table very similar to it in the book on page 190. This is something I would post, on the back of a quiz or something like that, so you can reference it. You don't need to memorize the electronegativities, but you do need to know how to use it. So a dipole moment can be a quantitative measurement of the polarity of a bond, but something just to keep in mind is a vector quantity, which means that it has a magnitude and a direction. So magnitude means size. The bigger the difference in electronegativity, the bigger the dipole moment, the stronger the polarity. Okay? And then the direction is always going to go towards the more electronegative atom. Okay? So, and then why symmetry comes into this is because your dipole moments, you're going to have individual ones with each bond. Sometimes with symmetry, they cancel each other out. Because if you have a dipole moment going this way and a dipole moment going this way and they're the same strength, those two arrows cancel each other out. Which would then, even though there's polarity in between the atoms, the molecule itself would be nonpolar. So, example of this is hydrogen and chlorine. Okay? Hydrogen had an electronegativity of 2.1, and chlorine has an electronegativity of 3.0, okay, which is a 0.9 difference. So the dipole moment goes from the hydrogen to the chlorine. It points towards where the electrons are going to spend more of their time. All right? That also means that where the electrons spend more of their time, you have that partial negative charge. And then on the other side, the hydrogen side, because the electrons don't spend as much time there, you have a partial positive charge. Okay, as far as drawing any of these symbols, I'm fine with you just drawing an arrow, and then I just kind of draw, I don't even know what, I guess it's kind of like a funky D when I draw it, as far as the partial positive and negative goes. Okay. So, some rules for determining if something is polar. Right? First off, you have to draw your Lewis structure. And then account for the shape. Okay? Because that shape is going to help us determine if there is symmetry going on here. Then you're going to use your electronegativity chart to check the electronegativity difference in each bond. Okay? So if you have any differences from 0 to 0.4, you consider that nonpolar. That's why carbon-hydrogen is considered a nonpolar molecule, because hydrogen is 2.1, carbon is 2.5, that's a 0.4 difference. Okay, anything from 0.5 to 1.7, we are going to consider a truly polar bond, and then when you get above 1.7, that's when you start running into your ionic bonds. Okay, so when we're sticking to just covalent, you shouldn't be, these ranges are going to be what gives you your polar molecules. Alright? Then the last thing to determine if everything falls between 0 and 0.4, regardless of the shape, is going to be a nonpolar molecule. If you find anything between 0.5 and 1.7 as far as electronegativity differences, then you have to check for symmetry. Because if all of the dipole moments cancel each other out, then we still call it nonpolar. Okay, so a couple of things just to keep an eye out for if it's nonpolar. Alright, if each bond in the molecule is nonpolar and there are no lone pairs, then you can just automatically say it's nonpolar. Okay, so when you have that 0 to 0.4 range and you have no lone pairs on anything, it's definitely not polar. If each bond in the molecule has the exact same polarity, okay, so say you realize that you have a 1.2 difference in all of your bonds, okay, but all of the bonds are attached to the central atom, and so like say something like this: carbon and chlorine, carbon tetrachloride. Chlorine is a 3.0 electronegativity, and carbon is a 2.5, so that does make all of these individual bonds polar, but carbon itself has no open spaces, so all of these dipole moments cancel each other out. Okay, so that would still, even though there's polarity within the individual bonds, the entire molecule itself is nonpolar. Okay, so that's where, if everything's nonpolar and you have no lone pairs, you can just go ahead and say it's nonpolar. When you have polarity, you're looking for a molecule that has no lone pairs on that central atom, because then that'll mean everything is canceling each other out. Okay? So that's where the symmetry in the shape comes in. As far as identifying polar molecules, if you run into any polar bonds and asymmetry, guaranteed it's a polar molecule. Okay, and then you just have to figure out what direction it's going in. Another time, when you run into the fact where you have lone pairs on the central atom, the only atoms that are going to not bond on all sides are the ones that have the higher electronegativities anyway. So when you run into lone pairs on that central atom, there's almost always an overall dipole moment for the molecule in some direction. Okay? Or if you run into bonds where you have different polarities. So like, say you have carbon attached to oxygen and hydrogens. Okay? There's no lone pairs on carbon, but we've got hydrogen, which is definitely different polarities than the oxygen. Okay? Or even if instead of those hydrogens you had in here chlorines. Okay? There's going to be a dipole moment because we have different polarity strengths pulling to the left and pulling to the right. Okay? So, to determine your polarity, first off, there has to actually be polar bonds, right? And then you have to check for symmetry. I know this kind of sounds repetitive, but it's a really important thing that you are going through those two steps. Determine if you have polar bonds, check for symmetry. So, some examples. We have boron trifluoride. Boron has a electronegativity of 2.0, and fluorine has an electronegativity of 4.0. So, I mean, this is even greater than the 1.7 range, so we definitely have dipole moments going on. The thing is, boron has no lone pair electrons on it. So we have these three dipole moments, but because of the shape of this molecule, they perfectly cancel each other out. Okay, so this is a non-polar molecule. Right? If boron had a lone pair, that would change the shape. Right? That would push the fluorines on the bottoms more towards the fluorine on the top to make room for that lone pair, and then we would have a dipole moment. Okay? So all of these individual dipole moments on the bonds, they cancel each other out, so overall, it's nonpolar. So, dipole moments that run into something that is asymmetrical. And you're going to run into asymmetrical shapes when you have lone pairs. Okay, so water. Water, the lone pairs aren't drawn on here, but hydrogen, those hydrogens are bent down because these electrons are repelling or repulsing the bonds down, as well as trying to spread out from each other. So that's why water has that bent shape. Alright, and that also makes it so that these two vectors, they're not pointing straight at each other, they don't cancel out. So overall, you can kind of tell they both point upwards. The overall dipole moment for the molecule is up. Okay? And that means on this molecule, I would be labeling the oxygen as slightly negative, and then the hydrogen end as slightly positive. Okay? So, when you run into asymmetry, it's going to be, you kind of go with the direction that is common with your vectors. Okay? Because the vectors, if you think about it, have a push. The one on the left has a push towards the right and a push up. The one on the right side has a push towards the left and a push up. These ones down here cancel each other out, leaving you with just that upward motion, which is why the overall vector points up. Okay? So, another example of where symmetry comes into play. Carbon and oxygen, definitely a polar bond, except in carbon dioxide, you have no lone pairs on your carbon. So this actually makes a linear molecule. So your dipole moments point in exact opposite directions, so they cancel each other out. Okay? Which means, overall, it's nonpolar. Last example is just to show you when you run into things with different polarities. Alright, so we have the carbon in the center, which carbon and hydrogen, technically, I mean, there's that slight polarity, but really we don't even consider that to be polar. So when you have these chlorine atoms, alright, and they all have a downward commonality in their pull away from the carbon, which gives you that overall downward dipole moment for the molecule. Now, if there were a chlorine at the top here, then this would be a nonpolar molecule, because that chlorine going up would cancel out all the downward motion of the partial downward motions of the other ones. But because we have a hydrogen on here, we have that asymmetry in the atoms, or different kinds of atoms on there, that makes this molecule overall polar, with the partial negative down at the bottom and the partial positive at the top. Okay. So, I don't want this to be too difficult. I'm going to stick to some pretty basic shapes. If you just remember, check for changes in electronegativity to first even figure out if there are any polar bonds within the molecule. And then, once you've done that, look for on that central atom lone pairs. If there's no lone pairs and everything attached to the atom is the same, then it'll be nonpolar. If there are lone pairs, then it's going to be a polar molecule towards the common direction of the most electronegative atoms. Okay, but we will definitely practice with this and bring any questions you have to class tomorrow. And of course, don't forget to do the online quiz.